Hello, so welcome to this next part of our course on the design of cluster randomized trials in cancer care delivery research. So in these next few sessions, we're going to be thinking about how we determine how many participants or observations we need in our cluster randomized design. And this particular session, we will be thinking about sample size determination in parallel arm cluster trials. So the objectives of this mini session are first of all to provide a brief overview of how we determine sample size or how we justify our sample size in individually randomized trials. We'll then go on to think about how we might extend this when we're thinking about sample size justification in cluster randomized designs. And this will include an introduction to a quantity known as the design effect, how we might infer likely values for the intra-cluster correlation coefficient, which turns out to be a very key parameter in sample size determination, how we might allow for varying cluster sizes, and importantly, how we make an allowance for designing trials when we only have a small number of clusters. And we'll end up by illustrating these methodologies on some example sample size calculations. So first of all, why is it important to determine how many participants we need in our trial so carefully? So it's important neither to over or underestimate the required sample size in any randomized trial. There are consequences of both under and overestimating. The consequences of underestimating the sample size might mean that we are unable to detect clinically important intervention effects, and this might mean that potentially beneficial interventions are discarded, perhaps never to be considered again. Now, underestimating the required sample size is far more common. Overestimating the sample size also has consequences, even though this is less common. So overestimating the sample size can mean that we might waste precious resources, and it might mean that participants are unnecessarily exposed to an intervention which might turn out to be harmful or perhaps ineffective. So before we start these calculations, there are a few things that we need to fix, things about our study that we need to have already pre-specified and decided upon. So two of these aspects include thinking about what the primary outcome is and carefully specifying that, and also thinking about what type of study design you're going to undertake. Other aspects that are also important will become evident as we progress throughout the course. So what study design will be used? Well, in this particular mini session, we are going to think about determining sample size both in patient randomized trials and in cluster randomized trials. So the first thing to consider is what is the unit of randomization? But it goes beyond that. We also need to consider other aspects of the study structure. So in a cluster randomized design, will we be using a parallel arm design, or will we include any crossover, perhaps at the level of the cluster or at the level of the individual? Now in this mini session, we are only going to think about determining sample size in parallel designs, but later sessions will cover sample size determination in cluster crossover designs, cluster designs with a baseline period, both under cohort and cross-sectional sampling. So a few other things that we're going to limit our consideration to here. So in this particular mini session, we're only going to think about sample size determination in parallel arm cluster randomized designs. So we're not going to include any repeated measures at all at the moment. But we're also going to restrict ourselves to trials where we are going to compare two treatment conditions, which we're going to label as intervention and control. We're also going to limit ourselves to superiority designs. That is situations where we're trying to determine if the intervention is superior to the control. We're also going to restrict our coverage to designs that have got equal allocation. So by this we mean a one-to-one randomization to intervention and control arms. and we're going to consider continuous and dichotomous outcomes. So before we start these calculations, we have to pre-specify and set a number of parameters. We call these the sample size parameters. The first of these is, what is our target difference? What is the effect size that we're hoping to detect? We also need to specify some measure of variation. For continuous outcomes, this means that we have to specify the standard deviation or the variance of the outcomes. And where we're considering a calculation involving proportions, we need to specify the control arm proportion. We also need to specify the desired level of power and significance. So by the level of significance, sometimes referred to as alpha, we mean the probability of making a type 1 error, where a type 1 error is the event of declaring there to be a significant difference, whereas in fact it doesn't exist. And we generally strive to maintain this type 1 error to be low, and it's typically set at 5%. The power, sometimes referred to as 1 minus beta, is 1 minus the probability of making a type 2 error, where a type 2 error is failing to detect or declare a difference to be significant when it truly is different. We generally try to achieve power of about 80 or 90%. So once those parameters have been set, we can move on to calculating the number of subjects that are needed per arm. So let's start by considering an individually randomized design. Now there are two basic sample size formula. The first of these formula on the top is the number of observations that is needed per arm to test two means, and the formula on the bottom is the number of observations needed again per arm to test two proportions, and this is all under the setting of an individually randomized design. Now we don't need to think too much about the detail of these formula, other than to note that they do share some commonalities. So they both are a function of our type 1 and type 2 errors here on the left-hand side. They're also both a function of the difference that we're trying to detect on the bottom of the fraction. And then they are both slightly different on the top of the fraction. The number needed and a comparison of two proportions is a function of the standard deviation of the outcome, whereas the number needed to test two proportions is a function of the two proportions that we're trying to detect the difference between. So those are the two basic sample size formula under individual randomization, and N represents here the number of observations or the number of subjects that are needed per arm. So why does this formula change when we are designing a cluster randomized trial? So in a standard patient randomized design, where we've randomized n subjects into each of our arms, the variance of the average outcome in each arm turns out to be this quantity here, sigma squared, which is the variance of the outcome divided by the number of subjects in each arm. Now in a cluster randomized design, this variance changes. And it changes to be a function of the variance of the outcome, that remains the same. N, number of subjects per arm, is actually replaced by the number of clusters per arm and the number of subjects per cluster. And it also increases by this quantity here known as the design effect. So 1 plus n minus 1 times rho, where rho represents the ICC, is known as design effect, sometimes referred to as the inflation factor. Now, this design effect is a function of the cluster size, and this other quantity known as the intra-cluster correlation coefficient, or ICC. This intra-cluster correlation coefficient quantifies the effect of clustering. It takes a value between 0 and 1 and is formally defined as the ratio of two variance terms. On the top of the fraction, we have the variance, which represents the within cluster variance, and on the bottom of the fraction, we have the sum of the between cluster variance and the within cluster variance. And the total variance of the outcome is equal to the sum of the between plus the sum of the within. And this is formally the definition for the intra-cluster correlation coefficient, or the ICC. So when we're trying to determine the sample size in a cluster randomized trial, let's start by assuming we're trying to test the difference between the two means. The required number of subjects in each arm is inflated by this design effect, where remember the design effect depends on the cluster size and the intra-cluster correlation. So it turns out everything simplifies quite nicely so that the number of subjects per arm, k times n, is equal to this design effect multiplied by the number that's needed under individual randomization. And then we can simply divide by n to determine the required number of clusters. So the required number of clusters k is equal to the design effect multiplied by the number needed under individual randomization divided by the cluster size. And then those same formula simply extend to the situation where we're trying to detect a difference between two proportions. So when we're trying to detect a difference between two proportions, the required number of subjects per arm, which is k times m, k is the number of clusters, m is the number of participants per cluster, is equal again to the design effect, multiplied by the same quantity, which is the number needed under individual randomization, and this all nicely condenses to be the design effect multiplied by n, where n is the number needed under individual randomization. And again, if we're interested in determining the required number of clusters, we just divide the whole thing by m. So the required number of clusters k is equal to the design effect multiplied by the number needed under individual randomization divided by the cluster size. So those are two nice simple formula for determining the required sample size under a cluster randomized trial for either testing the difference between two means or two proportions. But notice that those formulas depend on the intra-cluster correlation, the ICC. So we need to obtain estimates for the ICC. Now, calculations should always consider sensitivity across a range of likely values for the ICC. Now, when historical data are available, we can obtain tailored estimates using that historical data by fitting generalized linear mixed model to those data and estimating what we might call tailored or data-specific estimates of the ICC. A couple of things to note if this data are available. First of all, if only small data sets are available, so for example from pilot studies, the uncertainty associated with any estimated correlations from those data sets will be so great it will almost always render those estimates to be uninformative. The other thing to note is that when we are working with binary outcomes, the ICCs that we put into these calculations need to be on something called the proportion scale. And essentially this means that we fit linear mixed models, not logistic models, to estimate the ICCs. Sometimes historical data sets aren't available, and in those settings, we can try to obtain reports of ICCs for similar outcomes in similar settings. Now, it's important to note that the ICC relates specifically to the outcome of interest, and it's a measure of correlation between observations within the same cluster. So if we are going to try to obtain ICCs from similar outcomes in similar settings, those ICCs that are published in other trial reports will only be appropriate when they use the same or a similar outcome, when the unit of clustering is the same or very similar, when the setting and the context is the same or similar, and for binary outcomes, we must be careful to ensure that we are only using ICCs that have been estimated on the proportion scales and so do not come from a logistic model. Sometimes it's very difficult to find specific information on likely ICCs. So recommendations are in these situations that we use patterns observed from empirical studies. So important determinants of ICCs are known to be the outcome type. So ICCs for process outcomes tend to be larger than for clinical outcomes. Another important determinant is the setting. So ICCs in secondary care are typically higher than ICCs in primary care, for example. Cluster size is also important. So ICCs from smaller clusters tend to be higher. And prevalence is also important. So ICCs from more prevalent outcomes also tend to be higher. So moving on then to thinking about variation in cluster sizes. So far, the calculations or the formula that have been presented assume that the cluster sizes are the same between the different clusters. Now, often it transpires in practical settings that there will be some variation between the sizes of each of the different clusters. So in this type of setting, we need to modify the formula that we use to determine the sample size. Now, under the assumption that we are going to use what's known as a stratified randomization, where we're stratifying so that any variation in cluster sizes is balanced across the two study arms, then we can replace the average cluster size m by m multiplied by 1 plus cv squared, where cv squared is the coefficient of variation in the cluster size. So the coefficient of variation is defined as the variance of the cluster sizes divided by the average cluster size. And this is known to be a conservative approach to allow for varying cluster sizes. Now, there are some simple rules of thumb that might help us accommodate varying cluster sizes. First thing to note is that varying cluster sizes leads to a loss in statistical efficiency. We've noted this in earlier sessions. So one option to allow for this loss in statistical efficiency is to increase the cluster sizes. But it turns out that it's more efficient to increase the number of clusters. So a simple rule of thumb is that for most typical coefficient of variation in cluster sizes, we can compensate for those variations by increasing the number of clusters by about 25%. So that's an alternative, non-technical way of inflating our cluster sizes to allow for loss of statistical efficiency that will arise when we have varying cluster sizes. Other thing to be mindful of is a setting when we are working with only a small number of clusters. So in a parallel arm cluster randomized trial with a small number of clusters, we should use critical values from the T distribution rather than from the Z distribution. Now in our power calculations, this means that we have to change or set the degrees of freedom from the T distribution to 2k minus 2. And this approach is based on the assumption that these are the degrees of freedom that would be obtained if we carried out what is known as a cluster level analysis. Again, there are some rules of thumb that can help us here. So when we have varying cluster sizes, we can generally account for this by adding one cluster per arm. Or when we're working with a very small number of clusters, we can maybe add 2 extra clusters per arm, although that's considered to be quite precautionary. Word of caution about working in the setting of a small number of clusters. So a small number of clusters essentially means that we have a small number of randomization units. Now this can be problematic for a number of reasons. So most sample size formula that we have considered and will consider assume that we're working with a larger number of clusters, more than about 40. Many model-based approaches that we will consider in the analysis sessions and that typically are used to analyze these data also assume a large number of clusters, although things known as small sample corrections are available. The other thing to be mindful of is that a small number of clusters means an increased likelihood of a chance imbalance that can undermine the face validity of the study findings. Now, so far we've quantified the amount of clustering using the intra-cluster correlation coefficient. There is an alternative, and that's to use something called the coefficient of cluster variation, not to be confused with the coefficient of variation of cluster sizes. So the coefficient of cluster variation, or CCV, is equal to the ratio of the between cluster variance, sigma squared b, that we came across when we studied the formula for the intra-cluster correlation, to the true but unknown cluster mean represented by mu. Now this can be a very useful metric for quantifying the amount of variation across the clusters when we've only got cluster level means available from any data to estimate correlations. And it can also be a useful measure when the outcome is count rather than continuous or binary. One thing that we haven't considered so far is how do we determine this target effect size, this difference that we're trying to detect. Now there are various options, and these are not limited to but include other studies. So for example, a meta-analysis of similar interventions in similar settings might give us some hint at what sort of effect size we might expect. Pilot studies are sometimes used, although the uncertainty of any anticipated effect from a pilot study is often large. This is not typically a recommended approach. The other option that we can use is to specify what is the minimal clinically important difference. That is the smallest effect size that would be considered clinically important. Now this is an appropriate method, but it's not commonly used. A word of caution about setting this target effect size. So if we set the target effect size to be large, it will result in a smaller sample size. Now that can be quite appealing because if we set the target effect size large, that will keep the trial within budget, it will make it manageable, etc. However, if we set the target effect size to be much larger than which can be reasonably expected from that intervention, or one that is much larger from the true minimally clinically important difference, it will very possibly lead to an inconclusive study, one that has wide confidence intervals. Sometimes this is referred to as the power dance, so the target effect size is often manipulated until it achieves a reasonable sample size. But we have to be cautious with this approach because most observed effects that are realized in actual trials are often much smaller than the anticipated effect. So how do we implement these sample size calculations? Well, there are a number of different options. One option is to use a package like Stata. The function in Stata that we use is called power. Two means, for example, will compute the power of two means. There is also an RShiny app that we're going to look at here and a few other resources that are listed here. So let's start with an example. So in this setting, let's suppose that we've set the target effect size to be 0.2, that the variance of our outcome is 1. So we're working with what's known as the standardized effect size here. Let's suppose that we've set the significance level or the type 1 error to 5%, the power to 90%. Suppose that we know our cluster size, average cluster size is 20, and that we've, as a starting point, assumed the ICC is 0.05. The question then becomes, how many clusters do we need per arm? So step 1 is to work out the number that's needed under individual randomization. Various different ways that you can do this. One option presented here is to use a Stata function called power to means. It turns out that the number needed per arm is 527. We then multiply this 527 by the design effect and divide by the cluster size. We have to round up, and it turns out that the number of clusters per arm required K is equal to 52. So in that first example, we set the ICC to be 0.05. What happens if we increase the ICC, perhaps to 0.1? So everything else remains the same here. So again, we work out the number needed under individual randomization. We haven't changed the target effect size, the significance level or power, so that stays the same at 527. We now multiply the design effect, but the design effect has changed. So it's 1 plus 20 minus 1 times by the ICC, which has now increased to 0.1. And again, we divide by 20 the cluster size. And again, we have to round up. And it turns out that when we assume that the ICC is 0.1, the number of clusters required is 77. So increasing the ICC means that the number of clusters required has increased substantially from around 50 to nearly 80. Let's suppose we're working in a setting with a small number of clusters. So we're going to change the target effect size here to be larger, 0.5. Other things remain the same. We put the ICC back to the smaller value of 0.05. Again, we're asking the question, how many clusters do we need per arm? First step is to work out the number needed under individual randomization, and it turns out that this is 86, much smaller than in our first couple of examples because we're working with a much larger effect size in this example. So we take this 86 and we multiply that by the design effect, which again follows the same formula of 1 plus the cluster size minus 1 multiplied by the ICC divided by the cluster size. And it turns out that this exact value is 8.38. We have to round up to the value of 9. Now, because we're working in the setting of a small number of clusters, it would be precautionary and good practice to round this up by adding at least one extra cluster per arm to 10, maybe 11. So in settings when we're working with a small number of clusters, we must remember that we add an extra 1 or 2 clusters per arm to the numbers that these formula provide us with. The other thing that we need to be mindful about is how we modify these calculations to allow for varying cluster sizes. So let's suppose that we are working in a setting where we've set the target effect size to be back at the smaller value 0.2, variance to be 1. Let's suppose we set the significance level to be 0.05, power at 90%. Now suppose that rather than fix the cluster size, we fix the number of clusters per arm. And the ICC is fixed at 0.05, the first value that we used in our examples. The question now becomes, what is the required cluster size given that we have got 10 clusters per arm? So step 1 again is to work out the number needed under individual randomization. Back to the first example, so this is 527. Now step 2, it is possible to do this calculation by hand. So in our other calculations, we were working out how many clusters we need. Now we set the question up slightly different. The question now is, what is the cluster size? So it is possible to do this calculation by hand, but it turns out to be much more complicated. Also, Stata can't do it either. So one option is to use this R-Shiny app. This R-Shiny app here allows us to determine the sample size required for cluster randomized designs across a range of different types of designs, parallel, before and after, crossover, stepped wedge, etc. So apps like this turn out to be very useful when we want to go past the very simple sample size calculations for cluster designs. And we'll look more at this app in future sessions. So turns out that many cluster randomized trials are not using the appropriate methods to justify their sample size. And these results here present the findings of a review of sample size justification in 126 cancer cluster randomized trials published between 2011 and 2015. Green column represents an appropriate allowance for clustering. So a reasonable number, about 50% of studies, are making an appropriate allowance for clustering in their sample size calculation. But a non-significant minority of studies had no sample size justification or had an inappropriate justification. Also turns out that many cluster trials are not of the simple cross-sectional design that we have considered here. And so to determine sample size for the more common cluster randomized designs, more methodology is required than has been presented in this session. And we will come to those methodologies for determining sample size determination in a later session. So in summary then, sample size and power calculations for cluster randomized designs require information on intra-cluster correlations. Now that correlation has to be accounted for in sample size. If we don't, we might underestimate the sample size or overestimate the power. The calculations are very sensitive to these values for the ICCs, and so we have to be careful to ensure either we have an accurate estimate of the ICC or that we consider sensitivity across a range of different values. And in fact, it's probably wise to do both. Care is also needed when we're using these sample size formula in the setting of a small number of clusters, because those conventional power formula may not be appropriate. So here are some of the methods references that have been cited. Up next, we will be thinking about sample size determination in longitudinal cluster randomized designs.